Good evening and welcome to a lecture on cavity resonators. This presentation outline will cover the following number and look at the types of cavity resonators. Move on to resonators, as application amplifiers as well as filters, including that of microwave application. Now, a cavity resonator is nothing a metallic enclosure that confines electromagnetic energy. Essentially, you cover both sides of a rectangular or circular waveguides, and then you create some energy radiation by opening one of the sides. And again, you can actually output that signal by opening the other end of the waveguide. So essentially what usually happens is that your energy is stored inside the cavity, and this energy is what determines the equivalent transmission line of inductor and capacitor circuit. And because you're operating at very, very high frequency, the effect of resistance and conductance is not considered in waveguides. So cavity resonators are widely used in many applications, including that of making microwave filters, microwave oscillators, microwave amplifiers, as well as microwave oven systems. But each of these components, the filters, oscillators, amplifiers, can then be used in radar systems, satellite communication system, PSTN network, and so on and so forth. So let's look at the types of cavity resonators. Like I said, we've got three major ones. Though the ones that are widely used are the rectangular cavity resonators as well as circular cavity resonators. The entrant cavity resonators are basically a combination or the different shapings around circular cavity resonators, different shapings that can be achieved around the rectangular cavity resonators. So let's look at rectangular cavity resonators. What is of critical importance to look as we look at rectangular cavity resonators is what first of all, we already know how to calculate the cutoff frequency, which is the minimum frequency needed in order for you to propagate a signal through these cavity resonators. So this can be found by calculating FC equals C over 2 multiplied by the square root of M over A squared plus N over B squared, where A is the width of the rectangular waveguide, and B is the height of the rectangular waveguide. And then you've got M and N being determined by the mode, whether it's dominant mode or any other mode of propagating a signal in the waveguide. C, of course, is known as the speed of light, and is 3 times 10 to the power 8 meters per second. So, but for the rectangular cavity resonators, remember, you don't just have the height, which is denoted by B here, or A, which is the width of. It has got also a component called D, which is basically the length of the cavity resonator. So D being the length of the cavity resonator, and then of course, cavity resonators operate in a number of modes, and these modes are characterized by numbers M, N, and P, where M could be 1 in the dominant mode, N is actually 0 in the dominant mode, and P is another 1 in the dominant mode. So if you look at this equation here, you will notice that the mode is determined by these parameters M, N, and P, and so you can have, as opposed to rectangular waveguides where we had only TE10, where M and N was considered. In this case, we are introducing another parameter for cavity resonators known as P, which is essentially a mode that is specified by the distance D, which is the length of the cavity resonators. So let's move on. as we look at these cavity resonators, with this formula, we can actually calculate what is known as resonant frequency. And the resonant frequency FR is nothing but essentially the product of C over 2 multiplied by the square root of M over A squared plus N over B squared plus P over D squared. And the significance of the resonant frequency, this is essentially the frequency that is needed to operate a filter and oscillator in a stable state without any vibration, without any noise. So that's why we normally talk of resonant frequency, and it's very, very important in cavity resonators. Next, I want us to discuss now what is known as, or applying this equation, how we can actually do an exam just to calculate resonant frequency. But before we do that, maybe it would be important to take note of the conditions that are necessary for you to arrive at resonance. There are two major conditions. Condition number one is that the distance A, B, and D must be such that it is at half for wavelength. So if you check in these three equations here, if we made either A or D or B the subject, you notice that for your D there, it's essentially going to be found by lambda Z multiplied by P divided by 2. So that is just, and you can do the same for A, where A will be nothing but lambda X, okay, multiplied by M divided by 2. So what we get is that for resonance to occur, these dimensions A, B, and D must be such that they are multiples of half wavelength. And you can actually see here that this is basically the half wavelength. Equally, this one is the half wavelength. These are important conditions to be met. So this ensures that the field patterns inside the cavity fits. And it also ensures that the electric field and the magnetic field are equal to each other, and then they will begin to basically create some oscillation, which results in resonant frequency. The second condition is that the electric energy must be equal to magnetic energy. Again, this is very, very important. Remember, the electric energy is as a result of the capacitance that is formed across the walls of the waveguide, whereas the magnetic energy is as a result of the inductance that is formed along the walls, the waveguide in the direction of the electromagnetic propagation. Next, now I want us to look at an example where we can actually calculate for the cutoff frequency given the dominant mode and the resonant frequency given the values of P and D. So in this example, we are given a rectangular waveguide that has dimension, the width is A equals 3 centimeter, the height B equals 2 centimeter. And from these two, we can actually calculate the cutoff frequency, which would give us the 5 gigahertz. So this 5 gigahertz is the minimum frequency needed in order for you before you can actually propagate a signal. So it means that the signal you have to propagate in this waveguide must be above 5 gigahertz. So then secondly, in part B now, we're supposed to calculate the resonant frequency, given that D is 4 centimeter, and that now the mode is TE101, which means your M there is 1, your N is 0, and your P is 1. So substituting that in the resonant frequency equation, you have your M equals 1, you have also your your N here being equal to 0, your P equal to 1, and there you have it, your M as 1, and then substituting the values of A, which is 3 centimeter, and B, which is 2 centimeter, and then you put for D, which is also 4 centimeter. When we solve this, we basically arrive at a value which will be such that you have the speed of light 3 times 10 to the power 8 divided by 2, and then you square root that with 1 over 2, 1 over 3 squared. You can actually say 3 times 10, convert this into meters to the power minus 2, so that they are converted, the centimeters are converted into meters, plus the n, since it's 0, that means the second term will be 0, and then here you've got 1 over 4 times 10 to the power minus 2, everything there squared, and then the square root symbol basically. So this should be able to give you the resonant frequency, which will be above somewhere 6.2. Yeah, so you get a value of 6 point something gigahertz. And you notice that this frequency is actually above the cutoff frequency of 5 gigahertz, which means the signal will be able to propagate through this resonant, cavity resonator. Next, I want us now to discuss another important aspect with cavity resonators, and this has to do with essentially, okay, so just rubbing the screen here. So the next part is where now we look at what is known as the quality factor for rectangular resonators. The quality factor, by definition, is a measure of how well a resonator stores energy, and it's nothing but the ratio of energy stored to energy lost multiplied by 2 pi. And we normally want to have a high Q factor, which means that high Q factor means low losses and sharp resonance, while as low Q factor, it means high losses and broader response. The other way to look at quality factor is essentially the ratio of the resonant frequency to the bandwidth of a signal. And so if you are given, for example, the resonant frequency FR, like we calculated in the previous example, it was 6 point something, so let's say 6.4, then divided by whatever bandwidth is that you're given there, that gives you essentially the quality factor Q. So Q is nothing but the ratio of resonant frequency to the bandwidth. Okay, and bandwidth, we know that if you are given the resonant frequency FR here, at M2, then you've got other signals here, let's call it F1 and F2. Okay, your bandwidth will be nothing but F2 minus the highest frequency minus the minimum frequency, which is F1. So that gives you the bandwidth. So it means that if you look at this, where this is now your resonant frequency, and if I take this to be bandwidth, you would want as much as possible to have a low value for B. So the width between F1 and F2, the narrower it is, that means the sharper will be the high, the quality factor, and it actually signals a high quality factor. So the closer that bandwidth tends to 1, the higher will be the quality factor. And it means that at high quality factor, you have minimal transmission losses within a cavity resonator. That's why you don't want to have a high value of P in the cavity resonator, because high values of P means will translate in a low quality factor, and it is low quality factor would essentially means high losses, which is not needed in a cavity resonator. So discussing further on the quality factor, I think my next slide just shows that relationship of quality factor and the resonant frequency together with the bandwidth, where change of F is essentially your bandwidth. This is the most commonly used method in exams for calculating the quality factor. First of all, you need to know the resonant frequency, and then given the bandwidth, you can as well calculate the quality factor. Sometimes you are given the quality factor, you have the resonant frequency, then you are asked to calculate the bandwidth. So you can play around this equation for quality factor, which relates to resonant frequency and the bandwidth. Next, I want to discuss now circular cavity resonators. With circular cavity resonators, just like rectangular waveguide, these are just enclosed cylindrical conducting material which are intended to confine electromagnetic energy inside the circular waveguides. And the whole idea, again, the principle remains the same: confine the electric and magnetic waves inside the circular waveguide, make sure they're equal to each other, and then you create an opening on the sides, on any of the sides of the circular waveguides to create an input signal as well as an output signal. And what you're going to get is basically a signal of high oscillation that can be used in many applications, either as an oscillator, or you can push it as an amplifier or filter, as the case may be. So having defined this, let's look at how the modes of operation in circular cavities. Just like in a rectangular, you normally operate this in a transverse electric mode, as well as transverse magnetic modes. But let's take note, there is also an axial variation in the D direction, in the distance D direction, denoted by the letter P here. So you have the P factor that is being introduced in, again, just like we did. And this could either be, remember in the circular waveguides, the dominant mode TE, we say it is given by 1, 1, this 1, 1. So the dominant mode for circular cavity resonators will also be given by 1, 1, 1, where the first one is for M, the second one is for N, the last one is actually your P, as the case is being. So, okay. So you have now, having understood the three modes, let's now see how we can calculate the cutoff frequency as well as the resonant frequency in this type of cavity resonators, the circular cavity resonators. Okay. So to calculate resonant frequency, this can actually be achieved by taking into consideration the speed of light as well as the 2 pi there. Then you should have a KR divided by A, where A is the radius of a circular cavity resonator. Then you've got D here, which is the distance from the center of a circular waveguide, to where basically you've cut So if it is this kind of a scenario, you're talking of A being this radius, and if this was a circular, and you've cut it somewhere there, then D is the distance from that center there up to where the cavity resonator ends. So that's your D there. And then the P is essentially the axial mode number. That can be 1, 0, or any other number there, depending on the mode of operation of the circular cavity. So take note of this relationship for calculating. So you just need to know KR, like we discussed under circular, it's nothing but the Bessel function rule. And this changes where dominant mode is usually 1.841, but it can change depending on the mode. So usually K will be given. Then once you know the value of K, you can actually, know the value of A, you know your D, you know your P, you can calculate your resonant frequency. C will be as usual given by the speed of light, which is 3 times 10 to the power 8 meters per second. So let's do an example having understood the formula for calculating resonant frequency. By the way, for calculating cutoff frequency, how did we calculate cutoff frequency? FC for circular waveguide, the formula still remains the same. I think we should have calculated it using a relationship. Yes, this was, I think, calculated by 2 pi, 2 pi, 2 pi, 2 pi A divided by KR. Okay, so that's the cutoff frequency equation. Again, this was covered under circular waveguide. And then I think we also calculated cutoff wavelength, which was the reverse of this. I think it was KR divided by 2 pi, if I'm not mistaken, multiplied by C there. Yeah, something like that. So you need to have this kind of a relationship to calculate your cutoff wavelength as well as your cutoff frequency, so that you know whether or not a signal can propagate within that cavity resonator. That's the importance of the cutoff wavelength as well as the cutoff frequency. It's basically to know the minimum frequency you should propagate a signal inside a cavity resonator, inside a circular waveguide or rectangular waveguide, before you can actually think of propagating the signal. So let's do an example here. Or maybe before we do that, the quality factor, just like we did under rectangular, once you know resonant frequency, we know your bandwidth, you can calculate your quality factor. So now let's do an example 2. So given that the radius of a circular waveguide is 2 centimeters, and the distance from the center of that radius to where you've cut your resonator is 4 centimeters, and we are told that this is supposed to be operated in the TE11 mode, which means your M there is 1, your N is 1, then you've got your P, which is also 1. So our interest here is just to know the value for P. So since P is given as 1, so we can substitute it in this part of the equation. There's a 1 here for the mode. And then this KR is a constant given for the dominant mode of a circular waveguide, which is 1.841. You have your radius there, which is 2 centimeters. So you substitute there, your D is 4 centimeters, substitute. And then this is going to give you a cutoff frequency, a resonant frequency once you substitute this. So I'll leave it for you to substitute this and then give the final answer to this one as well. Next, I want us now to discuss applications of cavity resonators. Now, most of these cavity resonators are used to fabricate microwave oscillator circuits, basically to make an oscillator. Now, we know from our knowledge in electronics, we know that a simple oscillator will look something like this. There must be some DC source, plus and minus somewhere. Then you can put a capacitor here. Then you can have another inductor here. Normally you put an inductor here. And then you put another capacitor there. And then connect this. And then somewhere here you need a feedback resistor connected to your positive VCC. You need a positive voltage here. There you need a resistor. Somewhere here you need a transistor to form an oscillator. And of course you have an option to put another capacitor there. So let's call this capacitor C and this one C, which is usually the same value, inductor L there. Then you have a small voltage there. Okay, so this is grounded. Then, so here I'm using a BJT. Again, here you can have another resistor here. And then create an output here. And here, an output. So the signal you've generated here is a high frequency signal. Normally sinusoidal. Very high frequency signal. Now, how does this happen? So in this type of an oscillator, essentially what you've done, okay, I think here is grounded. So what you've done here is the key component that determines the frequency here. It's a value of your L here and the value of your C here, which is the same as this one. So you can actually calculate your resonant frequency, something like 1 over 2 pi. Okay. 1 over 2 pi multiplied by the square root of the inductor value, this value of an inductor there. And then these capacitors are in series. When capacitors are in series, they behave like resistors in parallel. So you're going to have C times C over C plus C. Okay, so the two are supposed to be multiplied and then square rooted. That's how we would calculate the value of that frequency in this. So the same principle under microwave oscillators. Now, instead of having capacitors and inductors here, remember we said the walls act as an inductor, the distance between the walls of a microwave act as capacitors. So, and you need that small voltage to initiate the original oscillation. And once the oscillation is done, then you need this transistor here to provide a feedback in order to make the oscillations continuous. Without that transistor and the feedback loop here, you would create an oscillation, but then it would die out. So to avoid it dying out, you need that transistor there. And that's how you get the oscillations. And then this is now what you feed. For example, in a transmitter, this output here actually goes to your modulator circuit, and then it mixes with the audio signal, which then that audio signal is modulated in accordance with the frequency of this carrier. So for microwave oscillators, cavity resonators are used to determine stable oscillation frequencies. You can, so in place of this is all substituted by the walls, the design of the cavity resonator itself. But then to create, you need some feedback and some amplification of that signal. So how do you do that? Normally, most of these microwave oscillators, they have what is known as the cathode and the anode inside. The cathode and the anode generates some kind of magnetic field, right? So it will create some magnetic field. And then you have also, and it is that component which then acts like an amplifier. The cathode and anode combination will act like an amplifier in the conventional oscillator, providing amplification and maintaining the oscillations, right? So normally that's a principle behind these cavity oscillators. You need to have a part. For the capacitor and inductor side, it is in the design of the cavity resonator. And then for maintaining the oscillations, you create what is known as the anode and the cathode component. And then there will be some circuit there. You will not need any resistance. Remember here, you don't need any resistors. The feedback itself is provided by that cathode anode combination. So all in all, that's why here I talked of a part of these oscillators, they act as feedback element. So the feedback part is in the design of the additional cathode and the anode. Once the design of the waveguide itself will create, once the electric field and the magnetic field are equal, there will be those oscillations. But to avoid the oscillations from dying, you create what are known as the cathode element there. So you'll see it when I give a diagram. So a good example of a microwave oscillator is what is known as a crystalline oscillator. I want you to go and look at the structure itself of a crystalline oscillator. You will find that there's some part where it has got cathode and just know that that part is acting as for feedback as well as for amplification of the signal to avoid the oscillations from dying. There are also what are known as magnetrons. Magnetrons are also widely used, especially in many radar systems, many satellite communication systems. All these are essentially there to generate oscillations, and these oscillations can be used to superimpose a baseband signal for the purpose of modulation and transmit and so on and so forth. Okay, so that's the application as an oscillator. Let's look at now their application in terms of amplifiers. You can also use them as amplifiers, right? And a good example is what is known as a klystron amplifier or traveling wave tubes. These are examples of microwave amplifiers, all made of tubes, cavities. You can see here there are cavities. In this diagram here, this is actually an example of a crystal amplifier. It has cavities, all these are cavities made shapes. Then you push in an input signal there. You want to amplify this signal, the output comes out as so if you had pushed in a signal of this nature, what will come out of here is a signal that has been amplified in amplitude of that nature. But you take note that the cavities themselves in the design, you have the inductive and the capacitive being created there. But in order for you to create the equivalence of a transistor and feedback loop, you need the cathode and the anode. In this case, the cathode is positively charged. It is what you have here, and the anode is what you have there. And once the signal comes here, it will be pushed in that direction, and then it comes out there as an amplified signal. So this design alone is actually similar to the way you have an amplifier. Remember, an amplifier in the conventional, you have something like this. It requires a small AC signal connected. Normally here you have a resistor, and then you may have a capacitor there, and then you have a transistor, and then either a resistor here or a capacitor. Again, this is okay. Then you have that. Then you have a resistor there. Then you have positive VCC there, positive voltage. Okay, so this signal here is V. It's AC normally that you want to amplify. The resistor there, capacitor there, right? Yeah. So here you can actually put in an inductor. Okay. So you have C inductor resistor. And then what will happen is that because you've pushed in that signal, once the base current flows there from the VCC, this signal gets amplified. The oscillations gets amplified by that transistor. And then in order to maintain the signal from dying, you have a feedback loop there. That is very important. And then you can put some output terminal there basically to create an amplified signal, which is also going to be bigger than the input signal there. So now in this case, the cavity resonators provide this part in terms of its design, the inductor capacitor part, basically in that format through the cavities that are created there. And then for amplification, you need the cathode and the anode design arrangement there. And then once the signal flows in that, from you have, this electric field coming, rotating between the cathode and the anode, then you create basically amplification, then you can output the signal there. So this is a basic principle of all amplifiers. The only difference between an amplifier and an oscillator is that with an oscillator, you are injecting a DC small voltage there first, right? Whereas for an amplifier, you need an AC. You're amplifying the actual, signal of interest, which is the baseband signal. So to maintain frequency integrity and to enhance signal strength, you make sure that you have this cathode as well as the anode, or the negative and positive polarity within the crystalline amplifier or traveling wave tube, which you are basically using to ensure that your signal is maintained in terms of oscillation and amplification. The next application where you use cavity resonators is that of filters. We know filters come in many formats. You have low pass filter, high pass filter, band pass filter, as well as band stop or band rejection filters. So again, what I have here is just an example. Now, what you notice from this diagram, there are a lot of openings there in this rectangular waveguide, and some slots have been opened there and there. So this could be the input there, and then that could be the output there. And then by putting these slottings, cavity opening up holes, or cavities, you are basically either creating a bandpass filter, low pass filter, as the case may be. So these microwave filters are widely used in satellite communication system, radar systems, filter in wanted and unwanted signal. Base stations in cellular communication, they all use that. So whether mobile communication, radar communication, satellite communication, they are widely used. What are the advantages? They've got high selectivity, low insertion losses, because you are not using active components like the actual inductor and capacitors. They can handle very, very high frequencies. So resistors here, you're not using resistors, which may cause heating. So because of that, they are very efficient components to use at microwave frequencies. So besides filters, you can also use these cavity resonators to create what are known as microwave oven application. The microwave which we use in our homes, it works on the same principle. There must be some part where you create these oscillations. And once you create these oscillations, you need to maintain the oscillations. And to maintain those oscillations, you need the filament there, which acts as a cathode negatively charged, and then you have the anodes here, which are positively charged. And once this happens, the oscillations which are created in this first part, right, are then channeled here, and then you've got what is known as a magnetron, this output part here, which will channel the electromagnetic oscillations that have been created here, which is a signal of high frequency. It will go through what is known as a waveguide there. You can see there's a pipe there that goes inside the cooking chamber of a microwave. And once these signals are put here and in isolation, then at the end here, you radiate this energy. And when this energy now mixes with the food, then it begins to basically cook. But to avoid it cooking from one side, normally where you have put the food, there must be you create a rotating mechanism so that the food is cooked in an evenly format. So that's again microwave at work. So we can see waveguides here being used. You can also see the use of the anode and the cathode to maintain the oscillations once they're created. And then you just channel those high frequency signals and then radiate them at the end and as you radiate them, heat will be generated. That heat is basically will react with the food. Then you have the food being cooked as it were. So that's essentially cavity resonators. They are widely used. And I'm hoping that if we undertake a tour, then we can actually see some of these components in real term. They're widely used. Any telecommunication company will have waveguides. Any mobile communication system has got waveguides. Any satellite communication system has got waveguides. Any radar communication system has got waveguides. So they are really widely used. Why? Because of the advantage of low losses, the advantage of operating at high frequency, therefore minimal noise. And so you can't do it without microwave or technology. So I think this marks the end of the presentation. But at the end, as usual, I have given some tutorials which I would want you to try. These tutorials just hinges on common calculations and also applications of